We will be talking about a few different definitions of acids and bases. I am not very concerned about whether you remember the name of the definition, but rather, can you identify acids and bases? So the Arrhenius definition is named after a Swedish chemist whose last name was Arrhenius. And under this definition, as an acid is a substance that produces hydrogen ions in aqueous solution. A base is a substance that produces hydroxide ions in aqueous solution. So HCl in its pure form is a gas, but when we dissolve it in water, it ionizes and it forms hydrogen ions and chloride ions. You put this in water, it forms hydrogen ions. Therefore, it is an acid. So HCl is a molecular compound. It's covalent. It's two nonmetals. This is not ionic. But when we put it into the water, it forms ion. It ionizes. So those hydrogen ions are very reactive. Let's think about, what is a hydrogen ion? Let's back up a step. What's a hydrogen atom? How many protons? One. How many electrons? One. So for a hydrogen atom to become an H plus ion, it loses its only electron. So what's left? A proton. Not even a proton and a neutron. Just a stinking little proton, right? So that proton is not real happy being alone, right? It's going to be very, very reactive. It's going to react with anything it can around it. So in an aqueous solution, what's everywhere? Water. Water, water, everywhere, right? So this hydrogen ion encounters a water molecule, and the water molecule has two lone pairs of electrons on it. And so this hydrogen ion can bond with the oxygen. This forms a coordinate covalent bond where the oxygen is supplying both of the electrons for the bond, and it makes this substance called hydronium ion. There are other species that exist, H with different numbers of H2O. They exist. We're not going to mess with them. So what we'll see, and I'm sorry if it's confusing, we'll see H plus aqueous and H3O plus aqueous used interchangeably. They mean the same thing. This one is simpler, but this one is more accurate, more representative of what's actually going on. But when we see H plus, chemist recognizes, well, you can't have just protons floating around. It's going to attach itself to water. I think of this proton, this hydrogen atom, hydrogen ion, as being a very young baby, right? Do babies go out by themselves? No, they can't walk, right? They can't move themselves. So you don't see babies, just hanging out on the sidewalk, right? Doesn't happen. Where do you see babies? You see babies with an adult, right? So this is the baby and this is the adult. And the adult's going to carry the baby around, okay? So we're going to see that we sometimes pass the baby back and forth, but the baby's never just by itself. Any questions yet? So the Arrhenius definition of a base. A base produces hydroxide ions in solution. So sodium hydroxide is a base. Dissolved sodium hydroxide, which is an ionic compound in water. We don't say it ionizes, we say it dissolves. It separates into, or dissociates, it separates into its individual ions, sodium ions and hydroxide ions. It produces hydroxide ions, it's an Arrhenius base. When the hydroxide ions formed by a base encounter the hydrogen ions formed by an acid, they will combine with each other and form a water molecule. So the acid and the base neutralize each other, or, annihilate each other. This is the second definition, Bronsted-Lowry. This is more widely applicable. This focuses on transferring hydrogen ions. Not does it form them in solution, but what's transferring hydrogen ions and what is receiving hydrogen ions. So the acid is a hydrogen ion donor. As we talked about, a hydrogen ion is a proton. So an acid is a proton donor, the base is a proton acceptor. So the acid initially has the baby, the proton, and passes the baby off to the base, who's the babysitter. Right? So the babysitter takes the baby and holds on to it for a while. Right? Takes care of it. So the base is the proton acceptor. HCl is an acid because it donates a proton to water. So here, instead of looking at this ionizing in water, we've got our HCl here, and we've got the water. And what happens is the hydrogen ion is transferred from the HCl to the H2O, forming hydronium ion. And what's left is the chloride ion. So this is really describing what is happening in the solution. We don't always write it this way because it involves more letters, right? We have to put the H2O in here, and it's easier to just do something like this. But this is what's actually happening. Any questions? Because that hydrogen ion is not left alone at all. It just goes directly from the acid to the base. It's not floating around on the sidewalk. So this definition also works for bases that don't actually have hydroxide ions, but still produce them in solution. So NH3 is a base. But if you're just focusing on hydroxide ions, you're going to, well, how can that be a base? It doesn't have any oxygen in it. How can it form hydroxide ions? Well, it's a base because it accepts a proton from water. So here we have ammonia, and here we have the water. The water is going to give a proton to the ammonia, an H+. So then we get NH4+, the ammonium ion, and hydroxide ion. So ammonia does form hydroxide ions in aqueous solution. Acids and bases always occur together because the acid is the one that started out with the baby, and the base is the babysitter, the one that takes the baby away, holds it, takes care of it. We're not child snatching or anything here. So if HCl is an acid and it gives a proton to somebody, somebody has to receive it, right? So when this acts as an acid, there has to be something else that's acting as the base. Otherwise, it cannot behave as an acid. So here, HCl is donating its hydrogen ion to its proton to water and making H3O plus and Cl minus. You get that idea? Remember oxidation reduction reactions? Yeah. Those were transfers of electrons, right? Something was oxidized, another thing was reduced. They had to happen together. Acids and bases are like that. You have to have both of them present. Some substances can act as acids or bases, and these are said to be amphoteric. So ampho is the same prefix in the word amphibian, right? Amphibians can live in the water and on the land, right? They can do both. So an amphoteric substance is one that can act as an acid or a base, and which one it does depends on the environment that it's in. So what if we take that Bronsted-Lowry acid-base reaction and turn it around? So in the previous slide, we looked at ammonia plus water makes ammonium plus hydroxide. Now we're looking at it in reverse. Ammonium ion plus hydroxide makes ammonia and water. Well, what's happening here? The NH4 plus is donating a proton to the OH minus to make NH3 and H2O. So here, the NH4 plus is acting as the acid, and the OH minus is acting as the base. The substance that was the base has become the acid, because the acid is the one holding the baby, right? You can't donate a proton unless you have a proton to donate. You can't pass off the baby if you're not holding a baby. So ammonium ion was holding the baby that water gave it, and now it can act as an acid and give that baby to something else. Are you okay with that? So we call those conjugate acid-base pairs. So when a base accepts a proton, it becomes an acid, and it's called the conjugate acid. An acid that has donated its proton becomes a base, and that's called the conjugate base. So conjugate acid-base pairs are any two substances related to each other by the transfer of a proton. They are different by H+. So ammonia can add a hydrogen ion. It can accept this proton, and it becomes NH4+. Now, here it did not have the baby. Now it's holding a baby, and so now it can act as an acid and donate or transfer that baby to something else. So this is the conjugate acid, is the pair with this one. H2O, if you take a hydrogen ion away from it, that's it acting as an acid, right? Donating a hydrogen ion, becomes hydroxide ion. This is a base, and that's an acid. This is a conjugate acid-base pair. Any questions? In each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. Don't get thrown off by the Bronsted-Lowry in front of that, okay? You can just ignore that word, identify the acid, identify the base, and identify the conjugate acid and the conjugate base. So how do we do this? We're going to look at our reactants, and then we're going to look at the products and see how they changed. We're looking for the transfer of an H+. So this one was neutral, and now it has a +1 charge, and it's got another hydrogen tacked onto the end of it. So how does this one become that one? Does it donate or accept? It accepts. So this is the base. It's accepting a proton. Where's that proton coming from? It's coming from the water. Water donates one of its hydrogens to this guy and becomes hydroxide. So this is the acid. Everybody okay on that? The base becomes the conjugate acid. Here's the base. It's the babysitter. You pass the baby off to the babysitter, and now the base is running around with the babysitter. I'm sorry, the base is running around with the baby. Hopefully not with the babysitter. That would be just wrong. But now this is holding the baby, and so it could pass it off to someone else, right? And then this is the conjugate base of that acid. This can seem confusing, and yet once you see how it works, it's actually really simple, which, you know, you could say that about most of chemistry except quantum mechanics. So any questions about that one? Let's look at this one. Which one of these is acting as the acid? HNO3, because here it was HNO3 and here it's NO3 minus. The difference is it lost a proton. So I'm not going to write the words out, I'm just going to call that A for acid. Well, if this is the acid, what does the other thing have to be? It's got to be the base. So we see that the acid lost a hydrogen ion and became this. What is this then? It's the conjugate base. So I'm going to call that CB. Here, the hydrogen ion accepted a proton, acting as a base, to become the conjugate acid. Okay? So conjugate acid-base pairs differ by one H+. The one that has the H+ is the acid. The one that doesn't is the base. Any questions? Okay, which pair is not a conjugate acid-base pair? Yeah. B is not. Well, what are we looking for? We're looking for, in a conjugate acid-base pair, two things that are only different by an H+. So we look at this one and this one. CH3,3N, CH3,3N, H+. Right? Okay, that's a conjugate acid-base pair. Which one's the acid? The first one or the second one? The second one, because this one has the H+. What about this one down here? HNO2 and NO2 minus. The only thing different is this one had an H and this one doesn't. So which of these is the acid? The first one or the second one? The first one. What's going on here? Well, these are real similar. Those were real similar, right? H2SO4, H2SO3. The difference here is an oxygen, right? Both of these have two hydrogens. This is not a conjugate acid-base pair. Okay?